We're going to take a look at a couple example problems using the kinetic theory of gases. Remember, kinetic theory of gases relates kinetic energy and temperature, and it says that 1/2 mv squared kinetic energy is equal to 3/2 Boltzmann's constant times the temperature in Kelvin. That is important that temperature's in Kelvin, it's the absolute scale. So we're going to go ahead and plug in what we know, but we're going to have to deal with that. So determine the speed of a helium atom, which we're given the mass of. So we have 1/2 6.67 times 10 to the negative 27th times v squared equals 3/2 Boltzmann's constant, which is 1.38 times 10 to the negative 23rd times temperature. Well, the temperature is 25 plus 273 to make it a Kelvin temperature, not a Celsius temperature. So that's 298. And then all we have to do is the math, and if we work this all out, we get a velocity equal to about 1.36 times 10 to the third meters per second, or that's 1.36 kilometers per second, which is really, really fast. Now, gas particles are not moving in a straight line distance. They're actually bouncing off of other gas particles. So this is VRMS, average velocity, but it's not just directly moving across the room, which is why diffusion of a gas happens slower than this, right? It takes a while for a smell to move all the way across the room because those collisions are redirecting the gas particle. All right, one more example problem. Determine the difference in internal energy of 1 mole of H2, that's hydrogen gas, and 1 mole of helium at 300 Kelvin. Well, remember, internal energy is actually determined by degrees of freedom. Helium is monatomic, and it's only got 3 degrees of freedom, so its internal energy is given by 3/2 times Boltzmann's constant times the number of particles times T. Or, if we like, we could use 3/2 times R times the number of moles times T, whichever, it's the same thing. But hydrogen, being H2, actually has 2 extra degrees of freedom since it can rotate. So its internal energy is given by U equals 3/2 R times N times T plus an extra 2/2 from its rotational freedom, R times N times T. So do these have the same internal energy at the same temperature? Turns out no, because that hydrogen gas can vibrate or rotate in more directions. It can contain energy in more dimensions, has more degrees of freedom. So this is pretty easy. Remember, R is 8.31 joules per mole Kelvin, and so we just take 3/2 times 8.31 times 1 times 300, so 3739.5 joules of internal energy. Whereas hydrogen, we're going to go ahead and essentially hydrogen has 5/2 R and T. So same thing, except that we're going to use 5/2, which gets us 6,232.5 joules of energy. So even though they're at the same temperature, because hydrogen has more degrees of freedom, it has more energy.